Okay, um, we are back again. So, on the last video, I said that on this one, we will continue um, solving these these matrices, the operation with these matrices using the GNU Octave environment, and this because um, this work by hand is very difficult. We um, it take a lot of time, and on the middle of the way we can on the middle of the operation we can commit mistakes. So on the last video we solved in Octave the example 2.16, this example, and we obtain a this matrix uh, with the exception of this element in this signal. All the rest of the elements which compose this matrix is correct, so we are getting a satisfactory result. Um, but as we are using a tool like the Octave, which is dedicated to do this type of task, which is numerical calculations. So I don't know exactly if this term, um, this element is wrong, since we are taking from the book. But today, solving this another example, we will confirm that the Octave is one of the best alternative to use to solve this type of um, operations of between matrices. So this is from the topic 2.9.2, which is cylindrical coordinates. So before we start to remember where all these matrices come from, which is of course is the definition of these transformations. So let's read again the example and also remember some concepts. First of all, when we are referring to cylindrical coordinates, we are referring to two linear motions and one rotation. So these two linear motions, they are translations and one rotation. So as you can see right here on this transformation equation, we have this transformation, this another transformation, and this rotation. So as the definition on a cylindrical coordinates, we are referring to two linear motions and one rotation. So we were solving this example, and it says that a cylindrical coordinate system includes two linear translations, sorry. So as you can see, we have two linear translations and one rotation. The sequence is a translation of R along the x-axis, a rotation of alpha about the z-axis, and a translation of L along the z-axis. So as you can see, we already have draw this description. We draw the coordinate system, and this is a analogy to a robot arm. So I said that we are supposing that this could be a robot that can do a translations like a different stage. So right here I said that is a mechanism with the ability to stretch itself and reach to this point, and after this movement of stretch about a ratio of R, it do another transformation, but now a transformation of rotation with some alpha angle, and then for the last last transformation about the z-axis, but I say that is not above the z-axis, it's outside, but on the same direction. And knowing how to read this description, we are able to not only draw the description, but also to write the transformation equation. And as I said, do this calculus, this operation by hand can be very difficult, and on the middle of the operation we can commit mistakes. So I said that we will use from here the Octave, but we can at least do some operations, so you see how you can do by hand, and with some we can compare with the use of the Octave. So let's see. Also, I said that considering that is a matrix in this SB and that a C matrix, first we will do a operation with A and B, and after the operation with C. Using the Octave, we will just type in form of line of code these matrices without have to operate one by one. So let's see how you can do this by hand. So we will multiply this line by each column. So is 0, 1, 0, 0, 0 multiplied by this column, cosine of theta, sine of theta, 0, 0. So is 1 times cosine of theta plus 0. Now you can see that these zeros will cancel all these other elements. So right here we will obtain just cosine of theta, and that is our first element. Okay, now is this line by each column. Now is this column. Okay, so let's change here, and minus sine of theta, cosine of theta, 0, 0. And again, we will just have this first element because these zeros are concealing all the rest of the elements. So is minus sine of theta. And we can use this for the rest of the operations. Right here, it's all 0. Right here, 2, 0. And now this this line. So now is 0, 1, 0, 0, and this column cosine of theta, sine of theta, 0, 0, and we will obtain right here just sine of theta, because this 0, this 0, this 0 cancel this, and this. So this element is sine of theta. Now, again, is minus sine of theta, cosine of theta, 0 and 0. And we will obtain cosine of theta. So this element is cosine of theta. Now we can do more easily 0 times 0, 1 times 0, 0 times 1, 0 times 0, so it's 0. And right here is 0 too. Okay, now is this line 0, 0, 1, L, and right here cosine of theta, sine of theta, 0, 0. And so we got right here 0 times cosine of theta, 0 times sine of theta, 1 times 0, and L times 0. So it's all 0. This element is 0. Now this column, minus sine of theta, cosine of theta, 0 and 0. And it's all 0 again. Now 0 times 0, 0 times 0, 1 times 1. So right here we will obtain a scalar value different from 0. Sorry, a element different from 0, not a scalar. 0, 0, 1, 0. So it's 0 times 0 plus 0 times 0 plus 1 times 1 plus L times 0. So is 0 is 1, the result of this element. Now this other column, 0, 0, 0, 1. So is 0 times 0 plus 0 times 0 plus 1 times 0 plus L times 1. So this element is equal L. Now this last line, zero, 0, 0, 1, and let's see. So 0 times cosine of theta, 0 times sine of theta, 0 times 0, and 1 times 0. So this element is 0. Right here, it's all 0 as well. For this column will be all 0. Just this column we will obtain a element different from 0. So 0 times 0 plus 0 times 0 plus 0 times 0 plus 1 times 1. which is equal 1, 0, 0, 1. Okay, let's see what we will get and compare with the result from the book and after with the Octave. So now times this other matrix. So again, this line by each column. Cosine of theta, sine of theta, 0, 0, times 1, 0, 0, 0. And that is equal, right here is just cosine of theta. So that is our first element. Sine times 0, cosine times 0 times 0, 0 times 0. Now this line, sorry, this column. Um, 0, 1, 0, 0, and right here we will be obtain sine of theta. So it's sine of theta. Now this column and is 0, and this one are 0, 0, 1. And is cosine of theta times r plus sine of theta times 0, 0 times 0, and 0 times 1. So is cosine of theta times r. So right here, well, cosine of theta times r. Okay, that's what we get. At least I'm doing something wrong. And now this will change the line. Minus sine of theta, cosine of theta, 0, 0, 1, 0, 0, 0. And that is minus sine of theta, changing the column, 0, 1, 0, 0, cosine of theta, cosine of theta. Now 0, 0, 1, 0, and it's all 0. Right here, 0. And again, r right here is minus sine of theta times r. And let's change the line again. Now is 0, 0, 1, 0, 1, 0, 0, 0. And right here, this element is 0. 0, 1, 0, 0. It's all 0 again. Now this third column, 0, 0, 1, 0. And right here we are obtaining 1. And right here is 0 again. And now the last line. Right here is 00 L1 1000, and we will obtain a value of 0. Um, 0100, it's all 0, so we will obtain a value of 0 for this element. Right here, this third column, 0010, and we obtain the value of L. And now the last column are 001, which is 1. Now let's compare with the result of the book. Let me see. A very important detail is that I'm doing this as this is alpha, and I'm calling of theta. So let's change. That's alpha, not theta. We have just to change this. Oh, sorry. Right here is not theta, it's alpha. So we have just to change this, just because of this. Because when I copy the characteristic matrix of rotation above the axis Z, I copy the matrix with the elements, and this data come together. So right here we will just change by alpha. Alpha, sine of alpha, right here is alpha, sine of alpha, cosine of alpha, cosine of alpha, minus sine of alpha times r. So instead of theta is alpha, just this. And let me see. Again, I have commit some mistake, and this right here is these elements. They are cosine of alpha and r cosine of alpha and r sine of alpha. I don't know why. Probably I'm doing something wrong. And now, this was part of the experience of doing this operation by hand. When we are working with matrices with order 2, 3 is more easy. Right here, these matrices are of order 4. They are 4 by 4 matrices. So as you can see, when we are operating large matrices, we can commit mistakes, and also it takes a lot of time. So now let's use the Octave and see what we get. Okay, I'm already got the Octave open, and as on the last video, let's use the specific package which contain the libraries, so we can do operations with matrices. Specifically, uh, use the data and the alpha without have to specify the length of the vector, which the axis, without specify parameters like p divided by 4, 6, and these parameters we substitute on alpha and data because Octave don't recognize values without being defined. So that's why we are using this package. So we have to type pkg and load symbolic. Now we use the command sims and specify the parameters that we wanted to use generically, like data, alpha, and now we are using also L, and right here I will use L, capital L, because if I type the normal L, it looks like the number 1, and also the R from ratio. Okay, now we have specified the generic parameters that we wanted to work, and now we have to enter with the matrices that we wanted to operate. I already have transformed the matrices in line code, so now we have just to copy and paste right here. Okay, let's bring the other ones. In the matrix C. Now we have to do the multiplication between them. C times A times B times C. And let's see what we get. And that is correct. It's the same result as we obtain on the book. So with that, we can conclude that the last the exercise 2.16, the element, this element that we are not getting a satisfactory result, that's strange to say, but as is from the book, is very confusing because but is that what we are seeing? Probably the book is wrong, or Octave is doing is having some conflict. I don't know exactly, but for this example, we are getting the correct values. So A times B times C the operation between these matrices and is the result of this transformation. And we are working with cylindrical coordinates R, alpha, L. So is cosine of alpha, sine of alpha, 0, 0, minus sine of alpha, cosine of alpha, 0, 0, 0, 0, 1, 0, R times cosine of alpha, R times sine of alpha, L, and 1. And as you can see, we are getting the same result using the Octave. So again, is a nice tool for your set of skills, and with the Octave, you are amplifying your ability to solve problems of this nature. And if I'm not wrong, I said that I was dividing uh, the video about Cartesian coordinates in two parts, and that is the second part using the Octave. But actually, we have to do one more thing before ending this example, but this we will do on the next video, because is what we're going to do is something that I have to explain um, to you. So for now is all, and thank you.